Hi everyone! In this video, I will be going over the USACO problem social distancing. So let me begin by summarizing the problem statement. Basically, there are N cows and there are M mutually disjoint intervals in which there is grass for grazing, and so the cows want to locate themselves at distinct integer points, each covered in grass, as to maximize the value of D, where D represents the distance between the closest pair of cows, and we basically want to find the largest possible value of D. So let's look at the sample input case so we can better understand what this is asking us for. So in the sample input, we're given that N equals 5 cows and M equals 3 mutually disjoint intervals. And so the intervals are from 0 to 2, 4 to 7, and 9 to 9. And so the answer to this specific input is D equals 2. So this is a maximum value of D that we can have, which means that if we were to arrange the cows in any position such that each cow is on an area with grass, then the maximum distance we can have between the closest pair of cows would be 2. And so one way to achieve D equals 2 would be if we put the cows at positions 0, 2, 4, 6, and 9. And so again, here you can see that the distance between the closest pair of cows is 2. Okay, so let's go back to the problem, and there's actually a few hints here that point towards using binary search. And so let me go over that. So first of all, the problem is asking us to determine the largest possible value of D. So we're searching for a value of D. And if we look at the range of values D can be, we notice that the intervals can be from 0 to 10 to the power of 18, which means in the worst case scenario, the largest possible value of D can be up to 10 to the power of 18. And so 10 to the power of 18 is a huge number. And so just because of this, it makes sense to use binary search. Because if you remember, binary search has an O of log n time complexity. And if you were to just take log of 10 to the power of 18, that's only 18. So it makes sense to binary search on the value of D when we're looking at time complexity. So let's go over how exactly this binary search will work. Okay, so let's say that the possible range of values of D was from 0 to 10, and we were binary searching for a correct value. So in a normal binary search, we would be checking if a target element is less than, greater than, or equal to the middle element of the array. And so the middle element of the array is right now 5. And so based on whether the target element is less than, greater, or equal to 5, we choose to either decrease the upper boundary or increase the lower boundary. So binary search in the context of this problem is slightly different because yes, we do have that same middle element of 5, but instead of checking whether it's less than, greater than, or equal to target element, we just now want to check if this value of D, 5, actually works. And so let's say 5 was a valid value for D. So let's say we can have D equals 5. So in this case, if we establish that D can equal 5, then that means we no longer have to search through 0, 1, 2, 3, and 4. Because again, we're looking to find the maximum value of D. So we want to search even higher. So basically, if the middle value does work as D, then we want to increase our lower boundary. And so in this case, we would reduce the array so we're only searching through these elements now. And so now the middle element in this case would be 8. And so again, we'll check, does the value of 8 work as a valid value for D? And let's say it doesn't work. Then in that case, we know that 9 and 10 would also not work. And so this is a perfect opportunity for us to decrease our array boundary, so decrease the upper boundary. And so in this case, we would now be looking at this array. And so what we want to do is that whenever we encounter a middle value that works as D, we'll store it in a variable. So let me just call this variable answer. And so initially, answer is equal to 5 because we've already established that 5 works as a middle value. And then we looked at 8 and we saw that 8 doesn't work, so then we decrease the upper boundary. And so now we have 6 and 7 in our array. And so let's say our formula for the middle value gives us that 6 is the next middle value in this array. And so if we look at 6 as the middle value, and again, we're checking, does 6 work as a value for D? And let's say it does work. Then we can update answer to be the maximum of what it is currently and 6. And so in this case, 6 is greater than what answer is currently, and so then we update answer to equal 6. And so again, since we've established that 6 works, we increase our lower boundary, and so now we're only looking at 7. And so let's say that 7 does not work. So in that case, we would decrease our upper boundary and then we would no longer have an array to search for. And so we can just return the answer we have stored in our variable, which would be 6. And so that's kind of how the binary search works for this problem. Rather than checking if our middle element is greater than, less than, or equal to a target element we're searching for, in this case, we're just constantly checking if the middle value for the range we're searching for works as D or doesn't work as D. And if it works as D, then we want to search even higher. So we would increase the lower boundary. And if it doesn't work as D, then we would decrease the upper boundary and search for a lower value of D that would work. And again, we want to keep on updating a variable with the answer as we keep on finding values that work as D. Now, the only thing left to do is to figure out how do we know if a distance D works or does not work. And the most optimal way of figuring this out would be to place all the cows starting from the very beginning of the first interval such that they are D apart. And if we are not able to place all cows before the end of the last interval, then that means the value of D does not work. So the way we can do this is basically we'll iterate through each of the intervals in sorted order, so from least to greatest, and we'll just try to place as much cows as we can within each interval. So for example, let's say we are checking if the value of D equals 3 works, and we're using this test case where n equals 5 cows. So again, we would place the first cow at the very beginning of the first interval, so at position 0. So again, our current position is 0. And so now we want to try to see if we can place any more cows within this first interval. And so we notice that the next cow must be at least 3 away from this first cow in order for D equals 3 to be satisfied. And so if we look at our current position at 0 and we add 3, we know that our next cow must be placed at least at position 3. However, since position 3 is outside of the first interval, we know we must move on to the second interval. Okay, so now we want to try to place as many cows as we can within the second interval. So already we've established that the next cow must be at least at position 3. However, the start of interval 2 is at position 4. So what we're going to do is we're going to essentially take the maximum of the current position plus D and then the start of this interval. And so in this case, it is 4. So then our current position now becomes 4 and we place a cow at position 4. Okay, now again, we want to try to place as many cows as we can within this interval. And so if we add 3 to our current position, we get 7. And so we notice that 7 is within the second interval, so we'll place a cow there. And if we add 3 again, we get 10, and we notice that 10 is outside of our second interval, so we move on to the next interval. So our last interval is from 9 to 9. And so we notice that now that we have moved on to a new interval, we want to use the same formula over here. So we want to take the maximum of the current position plus D, so that would be 10, and the start of this interval. And so the maximum would be 10. So we know that the cow must be at least at position 10. However, position 10 is outside of this third interval, and so then we have to move on. And since there are no more intervals left, then we are done. And so now that we've placed as many cows as we can, we notice that we've only placed 3 cows. And so since we were not able to place all 5 n cows, then that means the value of D equals 3 does not work. And so basically this is a strategy we can use to quickly figure out if a value of D works. We just need to iterate through each interval and try to place as many cows within each interval. Okay, so I'm going to be going over the code implementation for the problem social distancing now. So the first thing we're going to do is we're going to create variables for everything and input all the data we're given. So we're going to create a variable for n and m. And remember, n represents the number of cows and m represents the number of intervals. And so we also need a way to store the intervals. And so it actually makes most sense to use a struct in this case. And the reason why is because we will eventually need to sort the intervals from least to greatest. And so using a struct would make the most sense here. So I'm going to create a struct for the interval. And so within this struct, I'm going to create 2 variables. I'm going to create a variable for the start and for the end of the interval. And then the next thing I'm going to do is I'm going to create an array of these intervals. Okay, so now I'm going to input everything in. And then afterwards, I'm just going to sort the array of intervals. And so I'm going to do sort array plus m because there are m elements in the array. And so one thing to note is that we do need to add a Boolean comparator function for our third argument. So I'm going to create that right over here. So I'm going to do bool compare. And so in this case, we're comparing two intervals because we're sorting an array of intervals. So I'm going to do interval A and interval B. And so we want to sort from least to greatest interval. So we want to put the interval that comes first before the other interval. So I'm just going to do if a.start is less than b.start, then this should mean that interval A is before interval B. And so in this case, we would return true. Otherwise, we would return false. And remember, we return true whenever we want A to be placed before B, and we return false whenever we want B to be placed before A. And again, we want A to be placed before B if the start of A is before the start of B, because that means that interval A is before interval B. And so let me add this Boolean comparator function as the third argument to our sort function. Okay, so now that we've done the sorting, the next thing we're going to do is we're going to write the basic code for the binary search. And so we're just going to write like the general implementation code. And so we're going to have two variables, one variable for the lower boundary of the array and one variable for the upper boundary of the array we're binary searching on. And so initially, the lower boundary is going to be at index 0, and the upper boundary is going to be at 10 to the power of 18. Because remember, that's a constraint for D. D can be up to 10 to the power of 18 based on the constraints given for the intervals in the problem. And I'm also going to create a third variable for the answer. And again, keep in mind that we want to keep on updating the answer variable whenever we find a value of D that works as we're binary searching. So I'm going to initialize the answer variable to be -1 because we want to constantly take the maximum of the answer variable and the values of D we find that work. Okay, so now I'm going to write the binary search. So I'm just going to do while up is greater than or equal to low. So this means that we still have an array to binary search on. And then I'm going to create a variable called mid, which will represent the middle element, and that's just going to be low plus up divided by 2. So the average of the lower boundary and the upper boundary. And then we know that if this middle element works as a value for D, then we want to increase the lower boundary. And the reason why we want to increase the lower boundary is because we're searching for the maximum value of D. So if the middle element works as a value of D, then we want to search even higher to see if we can find an even bigger value of D that works. So what I'm going to write is I'm going to write if works of mid. And so I'm just going to create a function called works, and this function will be responsible for checking if mid actually works as a value of D. And so we'll finish that function later, but let me just create it here. Okay, and so again, we know that if the middle element works as a value for D, then we want to increase the lower boundary. So low becomes mid plus 1. Now the second thing we want to do is we want to update answer, because again, we found a value of D that works, and so I'm going to update answer to be the maximum of what it is currently and the middle element. Now we know that if the middle element does not work, then we want to decrease the upper boundary because we want to search even lower to find a value of D that does work. So in this case, I will just write else up equals mid minus 1. So again, we're decreasing the upper boundary. And so that would just conclude the binary search, and at the very end, we would just see out the answer. And now the only thing remaining to do is to finish the works function that will determine if a certain value of D actually works. Okay, so I'm just going to change this to be long because we know that the possible value of D can be up to 10 to the power of 18. And I'm also just going to call the input D instead of mid element. Okay, so I'm going to create two variables. One variable for the number of cows we were able to place, which I'm going to call counter. And I'm also going to create a variable for the current position, which I'm going to initialize to be a very large negative number. Okay, so the next thing we want to do is we want to iterate through all of the intervals in sorted order. So let me write the code for that. And so we already have a formula for placing the first cow in an interval. And so that formula is just the maximum of the current position plus D and the start of the interval. And so we know that if the maximum of this is less than or equal to the endpoint of the current interval we're on, then we know that we can place at least one cow within that interval. So I'm going to write the code for that. So I'm going to increase counter because that represents the number of cows we placed. And I'm also going to update current position to be this maximum. Okay, so this code places the first cow within an interval. And so we want to keep on adding cows within the interval for as long as we can. And so we know that the next cow we want to add must be at least d away from this first cow. And so we can essentially write that while current position plus d is less than the end of the interval, then we'll update current position to be current position plus d. So I'm just going to do plus equals d. And we also want to increase counter because that means we're placing another cow at current position plus d. And so again, we keep on placing cows until we reach the end of the interval. And so in that case, we'll just move on to the next interval in this for loop. And so at the end of this, we should have placed all of the cows, or as many cows as we can, within all of these intervals. And so we know that if counter, which is the number of cows we placed, is greater than or equal to n, then that means the value of d does work because we were able to place all n cows given this value of d. So in this case, we would return true. However, if this is not true, then we were not able to place all of the cows with a value of d, and so we know that the value of d does not work, and so we would return false. And so this concludes the code for this function works.